Okay, good. So I'm recording, and welcome to today's this afternoon's math session. Hope you're all well, and let's see what we can do today. So obviously the coursework is due today, so well done to everyone who's got that done in good time. Thanks for coming on to the session now. Hope the coursework was reasonable for you, and we will get that marked. What we're going to do is we're going to open up those Excel spreadsheets, and we will take a look at your work. We'll have a marking scheme, so we'll mark it, and we will write some comments for each of you. Not quite sure how yet. We'll either do it on the spreadsheet or we'll do it in the comments box on the Turnitin portal, so that you can see a mark and you can see what our feedback is, some tips on how to improve, and see where you got things wrong, see where you got things right. So hopefully you'll find that useful. So this week we've had the mini lectures, and the main thing we've been looking at is the probability density functions, and that's really what we've been aiming towards with much of this work, with the emphasis on making sense of experiments and understanding how to join together the sort of theoretical world of probability along with the practical world of trying to measure things and trying to work things out. That's what these things do. And we remember from the beginning that we had our experiment where we were tugging on some bits of metal to find a failure strength, and we could plot that as a histogram. We learnt about why the relative frequency density was useful for a histogram, and now we will see, or we have seen, that the probability density function of which is a theoretical idea of a theoretical thing, but you can see the commonality that that has to the histogram of the relative frequency density. And you can then use both of those things to calculate the likely behavior of things in the future, or the likely behavior of something, how something's going to behave after you've built it from a design. So that's really why it's so valuable. It's useful for experiments because it means we can take experimental data and turn it into a model which we can then use for future stuff. So the lecture or the class today is going to be one where we focus on probability density functions and check our understanding of them and check that we can use them. And today we're going to be focusing on some practical questions, and I'm going to ask you to do some work today. So you're going to need a pencil and a bit of paper and a calculator to try and work out a few problems. So we're going to go through some problems because I want to check your understanding of it. Some of you will have done this at A-level. This is material that you might see in A-level further math statistics modules, but I appreciate that the majority of you probably haven't done those, and so we're going to cover this material to make sure that everyone is familiar with it. Okay, so what we're going to do is some questions, and then I'm going to give you a multiple choice of some answers so that then you can input your answers into the web, and then we can see what you get right, see what you get wrong, get a feel for how you get on with that. So here we have a problem, which I'll just write out the basics of it. So we have people in a shop, and we're looking at how long it takes for people to queue to get served, queue time. We're going to call that T. It's a random variable. It's in minutes. So that's the length of time it takes for people to queue in a shop. And so this is something that we can represent as a probability density function. So someone has either measured this or they've worked it out somehow and come up with this model. Okay, there we go. So here we have a probability density function. We need to define it over all possible t. But there's only a particular region where anything happens, so everything else is 0. If t is greater than 0 minutes, but less than or equal to 9 minutes, then this function tells us the probability density function for how long it takes to get served. So that's c multiplied by 81 minus t squared. C is a constant. Okay, so our first question to check our understanding of these things, call that f of t, is to find out what is the value of c. So c is a constant in that equation, but what must it be? Okay, so please have a go working that out. I'll give you a couple of minutes to do so whilst I set up the quiz. So I'm going to give you some options. Okay, so if you go to www.menti.com, you can input this code, and that will give you some options. Sorry, that will give you the A, B, C, D options, and I'm going to give you some possible answers for what C must be equal to. Okay, so those are 4 possible answers. One of them is correct. Let's see what you think. All right, the votes are still coming in, so we've got quite a few. I will wait and let a few more people come in. Okay. So we've had 56 votes out of how many people we got today? 107 people. That's about half of you. So let's see what we have. So I will show the screen. You should be able to see that. There we go. So most of you think it is D, but there's a bit of a spread. Nice distribution. Some going for C, D and A. Clear majority. So, well, 42 out of 100 and odd. So at least more than a third of you know how to do this. So that's good. That's a good start, but I'd like to see that higher, and I'd like to see fewer mistakes on that one. So what do we know about this function that must be true? We know it's a probability density function, and so we know that over the whole range of possible values of t, that if you integrate it, then it must be equal to 1, because that's the whole possible space, and by definition it must be equal to 1 overall. So if we were integrating this over the whole space, well, from t from minus infinity to 0 is 0, and from 9 to infinity is 0, so we only need to be concerned of this interval 0 to 9, where we put in our function. And we integrate that. C is a constant, so we can take it out. 81t minus t cubed over 3 from 0 to 9, and that must be equal to 1. Okay, so that's the key thing you have to remember, that probability density functions over the whole range of possible times, they must integrate to unity. And so with that, t is going to be fixed by the limit, and so the only thing that's left is c. And so that's why we can determine what c is from an expression like this. Oops, not equals 0, equals 1. So we can tell that c must be equal to 1 over all of this. And if you top those numbers up, it comes to 486. Okay, good. I'm going to reset the quiz. Okay, so the next part is what's the cumulative density function? So what's the cumulative probability function of this? So we know what ft is. What is the cumulative probability function for this problem? So have a go working that out. I'll give you some options again. Okay, so we've got some options. Can you find the cumulative distribution? Okay, I'm going to show you the responses to that. There we go. So most people have plumped for A, and so it's reassuring that at least a third of you know how to do that. But if you're unsure, I'll tell you what to do. So the probability distribution tells us how that's distributed over time. So if you want to find the probability over a particular interval, you need to integrate this over that interval. The cumulative probability tells us the probability of it being at any point below t. So we integrate our function from minus infinity to t. And that tells us the accumulation of probability as we go from minus infinity to t. And so obviously as this t tends to infinity, then this must tend to 1 because the probability, cumulative probability of being somewhere within that space must be equal to 1. And so we integrate our function. We've done that once already, but instead of going from 0 to 9, we go from 0 to t. We've got our value of c, so it's 1 over 486 multiplied by 81t minus t cubed over 3. And then if you divide 3 by 486, you have t over 6 minus t cubed over 1458. Okay, so simple when you know what to do. So for the next question, I'll leave those results there so you can see them. So now we want to work out a few things that might be useful. So the next question. So what's the probability someone will queue for longer and 3 minutes. So given this information, we've got what's the probability that someone will queue for longer than 3 minutes? There are some options to have a go at. Someone asked, where's the minus infinity gone? Where does the minus infinity go? So I guess you're talking about that one there. So we're integrating our function from minus infinity to t, but our function is 0 from minus infinity to 0. And so the only bit we need to integrate from, as we did here, is from 0 to our top limit. So when it comes to integrating our function, we just need to integrate from 0 to t, which gives us this result here. So I'm going to check up on the quiz. Thank you, you're still there. That's good, still responding. So there's quite a lot going on at the moment. We've got, obviously the coursework is finishing. Your test for this module, we had to put it back a week. So you should have seen a message that the online test for maths, we've moved it back from the 9th of December to the 16th of December because of the travel window thing, where I believe you have been told about how you have to return home, or you should return home if you're in Manchester. So we didn't want to clash with anyone's plans for that. So we've moved our online test to that last week. Today I've been doing, this morning I was doing my first face-to-face session with third years for their process control module. And so that was very nice to be back in work and seeing some students and working through some problems. We've got our next face-to-face session is scheduled for next week. And I've forgotten which day it's on next week. I think it's Monday, isn't it? Yeah, it's Monday the 30th. So we will make some plans for that. Here we go, Monday the 30th. We're scheduled from 1 to 2:30 in the Reynolds building. What I'm going to do is I will put up a sign-in self-registration form on Blackboard so that you can book places. All the rooms have got limited numbers in, so there's a bit of logistical work. Depending on how many students want to come, we have to organize it differently. So what I'll do is I'll put a room available and people sign in to say they want to come. And then if that room fills up, I'll add another room and so on, so that we can staff it right and get the best rooms that we can and make it work as well as we can. Okay, so quite a few answers in on that one. I'll show you the screen. Here you go. Most of you went for B, that's correct. Well done. So what are we doing here? Probably someone will queue for longer than 3 minutes. So this is an instance where we can use the complement to help us. So first of all, you can think, well, what's the probability that someone queues for less than 3 minutes? That's easy because we've just calculated the cumulative distribution function, and that tells us the probability of somebody queuing for less than 3 minutes. That's going to be equal to 3 divided by 6 minus 3 cubed divided by 1458, which is a half, take away 1/54.
We can't see the paper. We can still see the screen.
So
Dr. Martin, your screen is blocking the paper.
that's 27/54 minus 1/54.
We can't see what you're doing.
26/54. But that's not what we want to know. We want to know what's the probability of someone queuing for longer than that. So the probability that they go for longer than that, well, they either have to be before or after that. And so we can use the complement. So the complement of that is equal to that. And then it's 1 minus 26/54. And that comes out at 0.519. Oh, I'm sorry, you can't see that. Oops. There you go. So here we go. So the probability less than 3 minutes is equal to F3. So you put 3 into your cumulative distribution function and you get 26/54. And the complement, or the probability of the complement of less than 3 is equal to the probability of greater than 3 minutes wait, and that's equal to 1 minus F3, which is equal to 1 minus 26/54, and that's 0.519. So good, well done to everyone who got that. Here we go for another one, a couple more to check our probability rules. So someone has been been queuing for 3 minutes already. What's the probability that they will be queuing Okay, so they've already been queuing for 3 minutes. What's the probability that they will be queuing for at least 7 minutes, given that we know they've already been queuing for 3 minutes? Can you work that out? All right, we're getting a few answers in, but not as many this time. What's the code again? Okay, there it is. There's the code. I'll put it in the chat as well so you can see it. Okay, let's see what you've got. Here are your answers. So this is much more of a spread. So we found something a bit more challenging. Fewer answers and more spread out. And my answer is C. And so well done everyone who put C. That's the answer to this one. So this one requires a bit more interpretation of the question to make sure we get the right form for it. I'll just shuffle that up. So it's not the case of what's the probability of someone queuing between 3 and 7 minutes. We have some prior information that they've already been queuing for 3 minutes. So the probability of them queuing for at least 7 minutes, given that we know they've already been queuing for 3 minutes, that's going to be higher than the probability of them queuing for at least 7 minutes for someone who's just arrived, because they've already had to wait 3 minutes. So the fraction, some fraction of people will have been excluded from that already. So let's see how we can write this first of all. What's the question saying? It says, what's the probability that our time is greater than 7 minutes, given that we already know the time is greater than 3 minutes? So that's how we can write it down. You can make it greater or equal to, but remember that for the continuous cases, it doesn't make a difference whether it's greater than or greater than equal to. Okay, so how can we do that? Well, we can use one way to do it is to use our rules of conditional probability. So the probability of that given that is equal to the probability of them both being true. Divided by the probability that t is greater or equal to 3. So that's how we can write it, just using the rule of conditional probability. But this one here is a bit trivial because, well, if you're waiting 7 minutes, more than 7 minutes, you must have waited more than 3 minutes already. So the probability of that and that is just equal to the probability that you're waiting more than 7 minutes divided by the probability that you have waited 3 minutes already. Now we've got these two things, and these are things that we can work out from our cumulative distribution function. So somebody asked in the chat, when do you use the different distributions? When do you use the probability distribution function? When do you use the cumulative distribution function? Well, you can use either because it's the same information in each, but use what's most convenient. And when you've got a problem like that, it's more convenient if you have access to it to use the cumulative distribution function, then you can just plug it straight in. So like we did before, then we say that's equal to 1 minus f7, and that's equal to 1 minus f3. And if you put the values in for that, I won't go through all of that, you get 0.13 as our probability. Okay, so that's one way of doing it. That's using the sort of formal conditional probability rules. Another way you could think about it is just to think about the actual distribution. So this time I'm going to do it not with the cumulative function. This time we're just going to think about what the distribution is actually doing so that we can turn this into something intuitive as well. So here we've got our probability distribution function f of t, that's t. So first of all, can we sketch what this is going to look like? That's our function there, it is c 81 minus t squared. Can we sketch what that looks like? There's the function there. So if t is equal to 0, here we go, I'll use that one. So if t is equal to 0, our function is 81c, so it's going to start up here somewhere, 81c. And when t is equal to 9, our function is 0 because 81 is 9 squared. So when t is equal to 9, it's 0, and it's a upside down quadratic like that. So that's what our probability distribution function looks like. And now we can interpret our question by looking at this as well. So it says, given that you've already been waiting 3 minutes, what's the chance you have to wait 7 minutes? Well, if that's 3 minutes, these are all the people who have waited more than 3 minutes. And then we can look, well, these are all the people who've waited more than 7 minutes. So you could say the probability of someone waiting more than 7 minutes, if they've already waited more than 3 minutes, you can see that all of the green area, that's all the people who've waited at least 3 minutes. And then the fraction of them who wait more than 7 minutes is that fraction there. So that area there is the probability of people waiting more than 7 minutes. And that fraction here is the probability of people who've waited more than 3 minutes. And then that ratio will tell us the probability that if you've waited that long already, that you'll end up in that section there where you're waiting more than 7 minutes. So you can do it with both of those, with both the PDF and the cumulative distribution function. Both of them enable you to solve it. You can do it using the conditional probability rule, or you could solve it by just thinking about the nature of that problem. And then there's one final bit for this. Part E. So what's the probability that two customers selected at random both queue sorry, I've said that wrong. I'll just redo that. So I'll make it clearer. So 3 customers are selected. So 3 are selected at random. What's the probability that exactly 2 of them queued for longer than 3 minutes? Okay, that's our last question. 3 customers are selected at random. What's the probability that exactly 2 of them queued for longer than 3 minutes? give some options. Good. Faster response on this one. Let's have a look. There we go. So most of you gone for B, and B's the right answer. Well done. Still some spread of opinion there. So let's check we understand why that's true. So we've got 3 people, and what's the probability that exactly 2 of them queued for longer than 3 minutes? So this kind of sounds like a binomial type of problem where you have 3 and you're choosing 2. So you can think about it like that. You can think, well, if you consider one customer, so any one of those customers, what's the probability? What's the probability that any one customer queued for less than 3 minutes? Oh, that's not going to help. Won't do it that way. So if 2 customers queued for more than 3 minutes, then the probability of one of them doing it multiplied by the probability of another one of them doing it multiplied by the probability of the one that didn't queue for more than 3 minutes will be that. So it's exactly 2 of them queued for more than 3 minutes. So that's 2 people queuing for more than 3 minutes, 1 person queuing for less than 3 minutes. So that's the probability. But there's more than one way for that to happen. Obviously, there's 3 people, and the one who didn't queue for more than 3 minutes, it could be any one of them. And so that's where the 3 choose 2 comes from. So that's the probability of any one of the ways it could happen. And then 3 choose 2 tells us how many different ways there are for that to occur. 3 choose 2. We have that from our conditional probability combinations and permutations data. That looks like that, and so it equals 3 in this case. There are 3 different ways that could happen. That makes sense. There's one person who's queuing for less than 3 minutes. That could be person C, it could be person B, or it could be person A. So that makes sense. And so then we multiply that by these things. So that's equal to 3 times, this probability is 1 minus f of 3, and that's squared because there are 2 of them, times f of 3, and that comes out at 0.39. Okay, good. Well, thanks to everyone who took part in the quiz. That was a little bit of practice on using these. We've not done the discrete probability distributions, but you'll see lots of questions on those in the weekly question sheets, and you'll get to chat to the teaching assistants next about that. So I'll wrap up this part of the lecture, of the class, and you can move to the problem classes. Now this week, Mariana is unwell, and so if you were in Mariana's group, please will you join one of the other groups today. And what I'll do in a second is I will just put some links to some of the other groups in the chat. Okay, so I've just added that link to the chat. So if you were in Mariana's group, there's a link there to Noah's group, so you can join Noah's group, and he will look after you today. Thank you.